Welcome to SciFlux. Here, you get daily coverage of the latest scientific research. Every day, we bring you new research in a clear and simple format so you can stay informed without wasting time. Like the video, subscribe, and leave a comment to stay connected and help this channel grow. And if you want each new research delivered directly to you, join the SciFlux newsletter. This paper explores how hidden energy losses undermine the efficiency of doubly salient electromagnetic generators, DSEGS, and how smarter control can fix it. DSEGs are robust and widely used, but their doubly salient structure creates inherently asymmetric magnetic fields. This causes uneven flux density, core saturation, and hard-to-measure iron losses, alongside asymmetric currents that increase copper losses. These inefficiencies quietly convert electrical energy into heat, reducing overall performance. To address this, the researchers first modeled the fundamental and harmonic behavior of magnetic flux to accurately calculate iron losses under different loads. They then introduced an online method to continuously estimate both iron and copper losses during operation. Building on this real-time visibility, they designed a three-phase asymmetric control strategy, allowing each phase to be optimized independently. Using a perturbation observation method, the system dynamically adjusts current and timing to minimize total losses. Experimental results confirmed a significant reduction in overall energy losses. The takeaway is clear. Precision modeling combined with asymmetric adaptive control can unlock substantial efficiency gains in DSEGS. This work shows that smarter control, not larger machines, is the fastest path to more efficient, reliable, and sustainable power generation. This paper explores a critical efficiency bottleneck in high-frequency power electronics: energy losses in inductors and transformers. As operating frequencies increase, eddy currents in windings waste power as heat, limiting performance and efficiency. The study focuses on PCB Litz wire, a compact alternative to traditional Litz wire. While promising, existing PCB Litz designs, usually limited to 2 layers, suffer from high DC resistance and low design flexibility. The researchers address these limits with 2 innovations: optimized winding layouts that reduce internal twists, and a scalable multi-layer integration method that distributes current evenly across 4, 8, 12, or more PCB layers, creating a true 3D lit structure. The results are decisive. Optimized layouts cut DC resistance by 31% without harming AC performance. Multi-layer designs achieved up to 43% lower AC resistance at 200 kHz compared to conventional high-capacity alternatives, while greatly expanding design flexibility. This paper examines a critical stability challenge in high-power electrical systems using parallel inverters with LCL filters. Specifically, it focuses on zero-sequence LC resonance, an instability that becomes severe when inverters operate at low switching frequencies, a common requirement in high-power applications. The study shows that conventional inverter-side circulating current feedback, ICCF control, fails under these conditions due to control delays. Through an equivalent admittance model, the authors identify the root cause. Control delay introduces a negative conductance in the active component of the system, which destabilizes the resonance instead of damping it. To address this, the paper proposes a passivity-based ZSLC damping method. By adding a controllable admittance component, the inverter's electrical response is reshaped to neutralize the negative conductance effect. This restores passivity and stabilizes the system, even with significant control delays. Experimental results confirm that the proposed method effectively suppresses circulating resonance currents in high-power scenarios. Overall, this work delivers a practical and robust control strategy that improves reliability, efficiency, and operational safety in large-scale power electronics, particularly in renewable energy and industrial applications. This paper explores a non-destructive way to look inside wood and detect hidden structural defects before they become safety risks. Researchers propose Polarization-Resolved Terahertz single-pixel imaging a technique that uses terahertz waves, positioned between microwaves and infrared, to penetrate wood without damage. By analyzing how polarized terahertz radiation interacts with wood's fibrous structure, the system reveals internal features that traditional inspections often miss. The setup operates at 0.29 terahertz and leverages single-pixel imaging to reduce system complexity and cost. The results are concrete. The method successfully identified internal knots as small as 3 millimeters, subsurface cuts just 1 millimeter deep, and even internal growth ring structures. This level of sensitivity demonstrates strong potential for industrial inspection and quality control. In short, this study shows that polarization-resolved terahertz imaging can deliver precise, low-cost, non-destructive evaluation of wood, improving safety, reducing waste, and enabling smarter inspection across construction and manufacturing. Every electronic device, from smartphones to satellites, relies on stable power delivery, with converters playing a central role. A common method for controlling these converters is current mode constant on-time control, valued for its speed and efficiency. Yet, traditional models often ignored slope compensation, a key element for stable operation, leaving engineers dependent on trial and error. This study revisited sampled data modeling, integrating external ramp compensation into the equations. The result is a simplified, accurate set of models that directly link converter performance, bandwidth, closed-loop gain, to specific circuit components. Engineers can now predict the effects of design changes with precision. Validated through simulations and experiments, these refined models make converter design faster, more reliable, and more efficient, providing a clear roadmap for optimizing power electronics across countless applications. Next paper talks about the rise of more electric aircraft, MEA, demands highly efficient, flexible power management to replace hydraulic and pneumatic systems. Managing multiple sources, generators, batteries, and loads poses a major challenge as traditional converters struggle with complexity, energy losses, and weight. Researchers address this with a 3-port high step-down converter, integrating a primary source, a battery, and the load port. Building on a cascaded buck design, it intelligently manages power flow in multiple modes, offering independent control between ports. A 600-watt prototype stepped down 270 volts to 28 volts at 25 kilohertz with high efficiency, low losses, and excellent component stress handling. This design simplifies wiring, reduces weight, and enhances reliability, providing a practical, robust solution for MEA power distribution and marking a key advance toward fully electrified efficient aircraft systems. Vehicle-to-grid (V2G) technology promises bidirectional energy flow between electric cars and the grid, but this requires highly reliable power converters. The CLLL-CDC to DC converter is ideal for this, offering efficiency, step-up/down capability, and full-load soft switching, yet traditional PI controllers struggle with real-world disturbances and parameter mismatches. Researchers developed ultralocal model-free Pulse-Frequency-Modulation, UMF-PFM, a real-time model-independent control strategy. By monitoring only system frequency and output voltage, it dynamically adapts to nonlinearities and disturbances, maintaining stable power flow. Simulations and experiments show UMF-PFM outperforms conventional methods, keeping voltage fluctuations under 1 volt even under challenging conditions. This robust adaptive control enhances V2G reliability, efficiency, and battery longevity, marking a critical step towards smarter, resilient electric vehicle integration into future energy grids. This paper explores advances in deep ultraviolet DUV photodetection, a critical technology for applications ranging from sterilization and flame sensing to space and security systems, where high sensitivity and strict rejection of visible light are essential. The study focuses on alpha-Ga 2O3, alpha gallium oxide, an ultra-wide bandgap semiconductor that is naturally solar blind, making it ideal for DUV detection. The key challenge has been producing high-quality thin films in a scalable and cost-effective way. To address this, the researchers used mist chemical vapor deposition, Mist-CVD, a low-cost, non-vacuum technique capable of producing highly uniform and crystalline alpha gallium oxide 3 films. Using these films, they fabricated a metal semiconductor metal MSM photodetector with standout performance. Responsivity above 1000 A per watt at 210 nanometers, an ultra-low dark current of 0.12 PA at 5 volts, a UV to visible rejection ratio of approximately 1 million, and response times in the millisecond range. Together, these metrics confirm both high sensitivity and extremely low noise, which are decisive for reliable DUV sensing. The takeaway is clear. Mist-CVD enables scalable, low-cost production of high-performance alpha gallium 2 oxide DUV detectors without sacrificing quality. This positions the technology for broader industrial adoption in environmental monitoring, medical sterilization, flame detection, and aerospace applications. It's a practical step toward making advanced DUV sensing commercially viable, not just academically impressive. Thanks for watching. If you enjoyed the video, please like, comment, and subscribe. Also, join our newsletter to stay informed with the latest discoveries shaping science and innovation. See you tomorrow with a new round of breakthroughs. Take care.